So thanks for joining us for this session on the changes and surprises emerging from East Antarctica. My name is Matt King, and I'm the Director of the Australian Centre for Excellence in Antarctic Science. I just want to tell you briefly about ACES, as we call it. It's a large investment from the Australian Research Council, where we're trying to understand climate risks emerging from East Antarctica and the Southern Ocean, funded out until 2025, hopefully for longer still. And we're focused on the physical climate system, but also the marine ecosystems. So we're working on everything from the atmosphere, the ocean, the sea ice, the land ice, and the solid earth beneath the land ice as well, because we recognise that Antarctica is a coupled system. It's a deeply complex system, and that you can't actually understand where Antarctica is going to go in the future without understanding interactions between those components of the system. There's about 150 people broadly in our team, from experienced researchers to early career researchers, and it's really a great group of people that I'm working with there. And so I'll be showing some of the work tonight will be from our team, a lot of it from just the best science that's going on around the world. I want to start with this slide because it really does speak to the importance of Antarctica, at least in terms of sea level change. We'll talk about other impacts of Antarctica later on. But shown on the graph is the amount of sea level that's locked up in Antarctica by sort of large drainage basin. And you see here that the sectors on the left-hand side of the map, the West Antarctica, which is the area that, as we'll see, is changing the most dramatically, could contribute about 4 metres of sea level rise. But the vast area on the right-hand side, from the centre through to the right-hand side of the map, is the vast East Antarctic Ice Sheet, which I'll be paying particular attention to. You add up all those numbers, it's 52 or thereabouts metres of sea level potential. And the message here is that we just don't want East Antarctica moving in the way that West Antarctica is changing, because there's just so much ice locked up in East Antarctica. Just one of the glaciers, and that's the one that some of our team are actually heading to the field right now to work on, is the Denman Glacier. That one glacier has enough sea level in it ice in it to raise sea levels globally by 1.5 metres. I don't know if you've ever stood on the edge of the Pacific Ocean or the Atlantic Ocean and just stared out over the vastness of that space. And just, if you have, just stop and think about what that would feel like or what would be required to fill up that ocean by 1.5 metres. Yeah, that's just the Denman Glacier. That's just one glacier. We're talking about vast amount of ice that are in these basins, and they have tremendous consequences for us. This is a graph of the current state of play of the changing mass of the ice sheet, and this is the thing that's relevant to sea level. On the vertical axis, we see mass change measured in gigatons. That's in billions of tons. And we see that while Greenland is the big changer there from 1992 through to 2021, adding about 5,000 billion tonnes of ice into the ocean that's not replaced by snowfall. We see that Antarctica in the purple line has added about almost 3,000 billion tonnes. And if you break that up into the different components of West Antarctica, East Antarctica, and the Antarctic Peninsula, you see that all those different areas are playing different roles. West Antarctica being the big changer, and East Antarctica perhaps growing slightly, but as we'll see, the overall appearance of East Antarctica is not really an accurate summary of the change that's underway there. Just did want to highlight here some of the different studies that make up some of those consensus estimates that I've shown on the previous figure. And here we see that if you look at, for example, the West Antarctic Ice Sheet, the WAIS area, there's 3 different studies and they all pretty much agree with each other. If you go across to the East Antarctic Ice Sheet, the EAIS, you see that the studies don't particularly agree well. One suggesting significant mass loss, one significant mass gain, and another one suggesting not much is really happening. So that's not a great situation to be in for East Antarctica. But just in the last few days, actually, a new study has come out that suggests that actually one of the reasons for that disagreement has been an underestimate of the amount of snowfall in Antarctica that affects one of those measurement types. And so if you actually do a better job of model the snowfall at much higher resolution, down at sort of a couple of kilometres scale, actually it suggests that actually it snows more in Antarctica, and actually as a result of that, some of those lower estimates are shifted up towards the rest of the group, and suggesting actually now we have a pretty good idea, and that we should have actually very good confidence in that we understand how Antarctica is changing, not just the whole Antarctic ice sheet, but the subcomponents thereof. So we know what is happening with these ice sheets with some confidence now. This is an animation of the changing mass of the ice sheet. It's from a satellite mission known as GRACE. It measures at relatively low spatial resolution, but monthly timescales, how the Antarctic is changing. And as the red colours emerge, you see the areas that are losing mass into the ocean and contributing to sea level. You see the big bulge on the left-hand side of the graph, but also off into the Antarctic Peninsula in the top left-hand corner. But you also see the oranges start to appear from East Antarctica as well on the right-hand side, indicating that that area is starting to lose mass. We see some blues emerge in the top of the figure, suggesting that there's increased snowfall in those areas. But this is where I return to that point that looking at the whole the number as a whole of Antarctica or a whole of the ice sheet, you miss these details, because it's when these coastal areas where they've got large glaciers draining into the ocean, when they start to change, then something is really happening here, and it's generally going to be as a result of the ocean forcing the ice sheet. We see the same patterns from other measurement techniques. So this is a map of elevation change from space of the ice sheet. The last one was mass change from measuring from Earth's gravity. And we see the same areas seeing the same sorts of signals. So not just as a whole of ice sheet level, but actually at the regional level, we actually have agreement between these techniques about the areas that are changing. And we see again these coastal margins where there are large outlet glaciers seem to be thinning, losing mass, driving up sea level. And in many cases, not so long ago, they were changing much less than they are now. Now, it would be also fair to say that the precise record that we have from the satellite measurements is only of the order 30 years long, 20 years in some cases, 30 years in others. And that's a relatively short time to be trying to separate out short-term variations in climate from long-term trends, and I'll come back to that topic later on. The key thing that is going to change Antarctica is the ocean. The Southern Ocean has been storing huge amounts of heat for now decades. About 70% of heating has been going into the ocean, into the Southern Ocean. And so that heat has been stored up. It's heat that's in the ocean that's not in the atmosphere, and it's been offsetting climate change globally. But now we actually have the situation of if the heat can get to the ice, then the ice will melt, and it will melt faster. And one of the keys to whether the heat will get in the ocean will get to the ice is what the shape of the seafloor is, through which that warm water can pass. And one of the sad situations that we have at the moment, actually, with understanding the Antarctic ice sheet and how it might change in the future, is we have, in some places, very few samples of data along the continental margin that would tell us whether there are these deep troughs that warm water can pass through. You can see that, in the sort of mid-Southern Ocean, here in the red colours, there's been a lot of cruises where they've sampled, measured the seafloor bathymetry, the shape of the ocean. But when you look at the areas along the margin of the ice sheet, there's a lot of blue, particularly in East Antarctica, indicating that actually there have only been 1 or 2 or 3 or 4 voyages into these areas. And I raise this simply because in what I will talk about in a moment, this should always cause us to be cautious about what Antarctica could do in the future, because there's a lot we don't know, but the things that we are finding out do seem to be going in the one direction. That Antarctica, the more we find out, the faster it changes, and the more we expect it to change in the future. The other thing is that low resolution data of this kind tends to smear out the deep troughs. And so we miss out on that deep information, and that's the deep troughs at which the warm water can pass through and get to the ice sheet. This is one area where we do have high resolution imagery from just a few years ago off the Vanderford Glacier and the one of the maiden test voyage of the Australia's new icebreaker, Noina, where it is mapped, this deep trough shown in the top right-hand corner, going down to a couple of kilometres below sea level. And that is a pathway potentially for warm water to travel along, get to the glacier and melt it back. And in fact, when we look at the point of where the glacier comes afloat and map that over time, we see that it's retreated by about 20 kilometres over the last 2 decades. So this glacier is retreating, it's thinning, it's behaving anomalously, and it has a very deep trough that until recently wasn't mapped. And the concern that we have is that there are many more of these deep troughs that are just waiting to be activated by the ocean and hence melt back the East Antarctic ice sheet. If we can look at the situation of grounding line retreat or retreat in advance for a number of other glaciers, we see that there are a number of glaciers in blue in recent decades that have shown retreat in East Antarctica, and retreat actually at rates that are not too dissimilar to the sort of maximum rates that were observed over the paleo time. Now, those rates were sustained over thousands of years, but we are seeing substantial change in parts of Antarctica, enough change to make us quite concerned about what's going on. One of the other things that has emerged just in the last year or two is that warm water seems to be encroaching towards Antarctica. So we have deep troughs, some of them not mapped, but we know that there is actually increasingly warm water moving from further away from the ice towards the ice, and it will start to access the ice along those deep troughs increasingly over time. Here we see around the coast of East Antarctica a lot more red than blues, indicating that in those areas there's been a profound warming of the ocean along the continental margin. And that isn't compatible with a stable ice sheet. Now, those of you who are astute observers of time series would have noticed there's a bunch of bumps and wiggles in this time series of mass change. It doesn't just go down as a straight line. There are periods where, even for short periods of time, the ice sheet might have grown overall. And so we set about trying to look into that, and we were interested in exactly what was causing those bumps and wiggles, but also what's behind the trend. This is where the AR6, the IPCC AR6 was not very confident about what was driving the change in Antarctica, stating that there was low confidence in attributing the causes of observed mass loss from the Antarctic ice sheet since 1993. There were some process-based studies that indicated it. Nonetheless, if you asked a survey of the global community, most people, I think, probably would assume that a lot of this was human-induced climate change. Fortunately, since the AR6, there has been some more evidence that actually helps resolve this uncertainty. A couple of papers from 2022 suggest while the retreat in West Antarctica and the Amundsen Sea abatement might have been naturally triggered in the 1940s, it failed to recover, probably because of human-induced warming since the 1960s and also human-induced ozone depletion since the 1980s. Simulations, very recent simulations of ocean warming in that area have certainly partly been driven, they suggest, by anthropogenic forcing. So there's studies that are continuing to emerge that actually confirms perhaps what most Antarctic scientists regarded as likely, that humans were driving at least a significant portion of the ice sheet change. There's still a lot to do in this area, and that I think should also cause us to take a cautionary approach to what we do with the climate system and East Antarctica, given the amount of information that we still don't have. So we're interested in the bumps and wiggles as well, and we're interested in how they responded to El Nino Southern Oscillation, and many people are familiar with these in terms of droughts and floods in either South America or Australia, depending on what mode or phase those are in. Another mode of variability in the climate system is the southern annular mode, which is really a contraction and expansion of the westerly winds that go around Antarctica. The interesting thing about the southern annular mode is that it's been moving towards its positive phase. The winds have been contracting around Antarctica since the 1940s, and that is almost entirely driven by humans. So if we were to find a southern annular mode fingerprint in Antarctic change, then it would suggest that actually maybe there is a human component to the change. And so that's what we set out to look for. And we found in this recent study we published just this year an indication that actually maybe 40% of the mass loss over the last 2 decades was attributable to the southern annular mode moving into its positive phase. And because that moving towards its positive phase and this contraction of the westerly winds around Antarctica, maybe that because that is caused by human ozone depletion and greenhouse gases, then there might be a pathway here to open up and attribute something of the order of a few tens of % of Antarctica's change to human activities associated mainly with snowfall changes. The other point I wanted to make is that surprises are emerging from Antarctica that has caused people to be surprised, and by people I mean scientists being gobsmacked by what they're seeing. This was a model prediction study from our team earlier in the year, published in Nature, where they projected that sometime by middle of the century, the formation of some of the waters that form part of the global overturning circulation would have slowed by the order of 40%. Now, the animation on the left sort of is a simplistic representation of that, but you can see where waters are being formed and being distributed, and that actually form part of a global system. Now, these waters transport heat, they transport nutrients, they transport oxygen. These are the things of life in the ocean. And our team identified, in a model projection that these would start to slow by about 42% by the middle of the century. Then within 3 months, there were 2 papers published, which were observational papers that were looking at exactly this topic. And actually both of them identified that already this production had slowed by 30% in two of the 4 areas in Antarctica. So the observations were decades ahead of the model projection. And we are already seeing a slowdown in the production of these waters, and this will have consequences for decades and centuries to come in terms of the distribution of heat, nutrients and oxygen in the global oceans. Another surprise was the dramatic reduction of Antarctic sea ice since 2017, but particularly this year, where you don't need to be a climate scientist to work out the red line is just very, very different to what we had observed over the last 40 years. It's not often that scientists start to use or try to use variants of the word flabbergasted constantly, but our best sea ice scientists simply couldn't understand what was going on, couldn't believe their eyes at what they were seeing. And another example of a surprise coming at us. And the sea ice plays an incredibly important role for the global climate system, reflecting energy back into space, helping produce the overturning circulation that I talked about as it forms and as the sea ice forms. the ecosystem dependence on it, the krill that feeds, sits at the bottom of the food chain, all of these things depending on sea ice. And it would be fair to say that my team and others around the globe are really very concerned about what they're seeing here, and actually very concerned about what's going to happen in the future. You could look at that graph and say, well, by the end of 2023, it's sort of caught up to where the trend was, but that sea ice will be, in the main, thinner than usual and primed to melt faster than usual, and we would expect that curve to drop very quickly, more quickly than usual. Colleagues in Australia have noted that the sea ice extent shown in the top right-hand corner here was perhaps growing a little bit over 30 years or so. Then it seemed to move into a high state where there was more sea ice than normal, and then it fell off a cliff in about 2017, and again in 2022, where it's entered a new phase. And the bottom plot is one of the oceanography profiles, suggesting that actually it is a new state and that the ocean is structured in a different way. It's warmer than normal. It's certainly the surface. Something has changed, and the concern is what comes next. Another surprise, this is, we're all within 12 or 18 months of each other, a 40-degree heat wave in March 2022. The air temperatures didn't really breach zero because it was cold enough, but this is a heat wave covering an area of East Antarctica larger than India. And just in any other place on Earth, we would not be able to understand what we were experiencing with a 40-degree heat wave. Unprecedented in the last 40 years. It's possible that it's occurred before. But these are things that we don't know about Antarctica that keep coming at us, and that's part of the story. We don't know everything about this place, and that should cause us to be cautious. A few days later, the Conger Ice Shelf, fortunately not a super consequential ice shelf, but a few, 10 kilometres by 20 kilometres, maybe 200 metres thick, broke up in the matter of days, splintered into 1 million icebergs. But even then, that would affect the local ecosystems. The iceberg production will change the local oceans. This might be the beginning of a more substantial change of this sort in the future, as we would expect to see larger and more consequential ice shelves break up and stop holding back the ice that's upstream, and hence allow for greater sea level contribution. And as we move through to think about the future, I do so saying that actually the best of our models can't reproduce always what we're seeing, and often Antarctica is changing at a faster rate than the models project. For example, if you take the map in the bottom right-hand corner on the left-hand side underneath the observations there, you see areas that are changing present day quite dramatically in Antarctica. The models used in the IPCC projections don't reproduce the changes in all of those areas. In fact, in some of those areas, they suggest that actually there's no change going on. And so that should lead us, while this is the best available and these are really state-of-the-art models, it should cause us again to be cautious, because things are happening faster than we expect them to happen, and our theoretical understanding is lacking. If you have a look at the time series of projection in the top right-hand side, you'll see the observations for the first few decades, and then the projections take over. You see some projections actually suggest the Antarctic ice sheet will grow slightly. Most of them suggest that Antarctica will contribute to sea level over this coming century. You'll see that there's a significant uncertainty. That uncertainty depends largely on the climate forcing that we as humans decide to place on it. But there are other uncertainties in terms of we just don't know all the physical processes. They're not all captured in the models yet. But I'm hoping to convince you that actually we should expect that number perhaps to get worse, given that given the number of processes that are not captured. The potential future in the long term, and here we're talking about effectively permanent on human timescales effects on Antarctica, well, we can perhaps have an insight from that from looking at the mid-Pliocene warm period in the bottom left-hand side, the last interglacial, where we see Antarctica not looking like it looks now. Substantial areas of deglaciation, possibly adding many, many metres to sea level. We can see this in this series of projections, where we first see a projection for 1.5 degree climate out to 2100 in the blues. You can see there the Antarctic ice sheet contributing about 0.1 of a metre. That's still going to flood millions of people, and it permanently affects their livelihoods and their homes, their social structures. And actually the rate of sea level rise is still increasing through that period of time, but it does buy people time from the worst of it. If you go out to 2300 at 1.5 degrees, you see you get to about a metre of sea level rise. But it's when you contrast it with, say, 3 degrees of warming, which is certainly within play at the moment, we see sea level rise from Antarctica of about 1.5 metres by 2300. And in the really high scenarios, heading towards 10 metres of sea level, and some model projections out to 15 metres of sea level by 2300. So we don't want to be in this space. We want to keep Antarctica pretty much as it is, and the 1.5 degree scenario is our best chance of getting there. I'm going to skip over that slide because that hasn't quite worked out. There's been some recently some model scenarios of the ocean in that key area of West Antarctica that I mentioned, the Amundsen Sea embayment, where the model looks at ocean warming in that area over the next century, associated with 1.5 degrees, that's in the blue, 2 degrees in the green, and greater warming in the other colours. And you can see that the 1.5 degree scenario, while it still warms the ocean in that area, it's the one that breaks stride the earliest and by a significant margin. 1.5 degrees provides a distinct advantage and actually a hope that the Antarctic ice sheet will change slower than the other scenarios. The other important thing to note is that ice sheets are good at melting, they're slow at forming. And we can see that in the climate record from the past over the last 150,000 years or so here, where the decay from the peak is generally slower. And so that's the forming of the ice sheet as the sea level's lower. But actually the rising of the sea levels, the melting of the ice sheets, happens a factor of, 2 or 3 faster here in this figure. Melting is much easier than growing an ice sheet. And we are dealing with things that can't be put back in human timescales. So I really wanted to stop with this figure again, that we don't want to mess with 52 metres or 58 metres of sea level rise. Changes are already underway. Humans may not have driven all of that change, but at some stage, the human forcing and the ice sheet response will take over as the dominant signal, if it hasn't already. We know that there's increased snowfall over parts of Antarctica. That's consistent with ocean warming and increased capacity for the atmosphere to hold moisture. And when it gets to Antarctica, it snows more. We know that there's increased flow and melt. We know that there's increased warming of the oceans around Antarctica. And in many cases, it's faster than we can reproduce in our best models. And to me, all of that uncertainty suggests that we should be cautious about Antarctica and we shouldn't be playing dice with it. And with that, I shall finish. Thank you very much. So I'm happy to take questions. Yes.
With what confidence can you say that the heat wave in 2022 caused very up the wrong direction?
Look, I think it could be pure coincidence. I think there has been some work that suggested a mechanistic aspect. that was retreating and collapsing slowly over decades. It may well have been a final straw that broke the camel's back situation. It might have been a straight coincidence, and I dare say we may never know, because it was one of those places that no one ever really went to. It was poorly understood to begin with, but it's the sort of thing that we will expect in the future. So it's a visual aid for us to understand that actually dramatic things happen in Antarctica. It isn't, and actually even just a few decades ago, scientists thought Antarctica was a pretty boring place that changed over thousands of years. Within 2 or 3 decades, we've realised that actually things can change overnight in Antarctica. And that's just a good reminder for me that actually that's the case. Yeah.
How strong do you think awareness is amongst our decision makers about this? I mean, there's been lots in the media about the sea ice and so on, but is that message getting across to where we need it to be?
Look, I think Antarctica is very long way down the list of people's thinking when it comes to climate change. I think there's a sense of it's a long way away. Yes, we sort of broadly understand something about sea level change, but I really don't think they understand that every day a slice of Antarctica laps up against our shorelines. That right now, today, Antarctica is slowing the global overturning circulation, the thing that makes our climate the way it is. So I'd say there's a very limited exposure to that, to the ice sheet, to the oceans, but to the ice sheet, absolutely. Okay. Well, if there's no other questions, more than happy to wrap it up there. Thank you very much.